I want to give you one more example of an inner product space, and then I want to talk about some properties of inner product spaces. So the example I'm going to give you is the vector space Pn, which is the polynomials of degree n minus 1 or less, and we're going to define the inner product in the following way. For P and Q in our vector space, and x1 through xn, these are n distinct real numbers, where this n, you can see that this n corresponds to this n. So if this is P3, we're going to have 3 distinct real numbers, and when I say distinct, that means we don't repeat numbers. And they can be positive or negative. The only property is that they have to be real and they have to be distinct. So that's really important. And how we're going to define this inner product is we're going to say it's the sum, I is equal to 1 to n, of P of xi times Q of xi. I claim that this is an inner product on this vector space V. So let's just make sure we understand what this means. So our example is going to be, let's say, P3, which is polynomials of degree 2 or less, which is polynomials that look like this: a plus bx plus cx squared, where a, b, and c are in the real numbers. And we need to pick 3 distinct points. So let's say x1 is 1, x2 is 3, and x3 is 0. So all of these numbers are different, and as long as they're real numbers, you could also do something like 1.5, or you could put a pi here and a negative 12. Whatever you want to put, as long as you don't repeat numbers. Okay, and now we need to pick 2 polynomials. I'm going to say 1 minus x squared. That's a polynomial in this space. And let's go with, I don't know, let's say 3 plus 2x. Then the inner product of P and Q is the sum, I is 1 to 3, of P of xi times Q of xi. Okay, well, we need to evaluate these polynomials at these 3 points. Let's do that. So P of x1 is 1 minus 1 squared, which is just 0. P of x2 is 1 minus 3 squared, which is 9, so this is a negative 8. And P of x3 is 1 minus 0, which is 1. Q of x1 is just 3 plus 2 times 1, so that's 5. Q of x2 is 3 plus 6, which is 9. And then Q of x3 is 3 plus 0, which is 3. So then the inner product, we start with the first one. So we have 0 times 5 plus negative 8 times 9, and then 1 times 3. Okay, let's make a little line here. So this is 0, negative 72, and 3. So this is 69. Okay, and that would be the inner product of P with Q. So now that we understand what this is and how to figure out the inner product of two polynomials, let's check that it's actually an inner product. So it passes the three properties for a map to be an inner product. So let's make a little bit of room here. So what are those three properties? Well, first off, we need to make sure we have a map that takes our vector space. It picks a pair of vectors and sends it to the real numbers. Well, it does here because you're plugging in each xi, you're going to get a real number times a real number, and you're summing, you're going to get a real number. And this p and q are from our vector space. Okay, so that's fine. Then we have to check that, well, let's use a different letter other than x. Let's say p with p is greater than or equal to 0 for all p in our vector space. And if the inner product of p with p is 0, this is true if and only if p is 0. The second thing we need to check is that for any p and q, not just those two the p and q I wrote earlier, but for any polynomials, that the inner product is symmetric. And then the last thing you want to check is, let's go with H, that the inner product is linear. Oops. Okay, so maybe we can, of course on your homework you would want to write this all out, but let's talk about it and see if we can reason through this one. So let's do number 2 first. Is it true that this thing is symmetric? Well, let's look at this. It doesn't matter if we take two real numbers and we multiply them, like a times b, that's the same thing as b times a. So from this definition, here, let me erase this. This is actually equal to the sum, I is 1 to n, of qxi times pxi, which is, by definition, this inner product. So this is fine. I don't know why I put an x here. I think because I was thinking about x, but that should be a p. Sorry about that. That's a p. So this is symmetric, so that's fine. Okay. What about, let's say number 3. Well, if you multiply, let's write this out. If we take alpha p plus beta q with h, then this is I is equal to 1 to n of alpha p plus beta q of xi times h of xi. But then because what we know of functions, we can distribute this. We can make this the sum of alpha p of xi, h xi, plus beta. So let me keep the beta in the sum for a second. Beta of qxi, h of xi, because you know that you can distribute this h of xi and that a summation breaks over addition. And then you can also pull the constants out of the sum as long as they don't have an I associated with it, then that's fine. You can pull anything that doesn't have an I out, and you're going to get this right here. So this works. And then the last thing is you just have to check that if I take the inner product of P with itself, well, by definition, that's P of xi squared. And obviously these are real numbers, we're squaring them. When you square real numbers, it's going to be positive or 0, so definitely it's going to be greater than or equal to 0. And also, the only time you're going to get 0 is if every single one of them is 0. So it does pass the properties of an inner product space. So it is an inner product. All right, let's move on. We've seen a lot of examples of inner product spaces. Let's talk about some basic properties. And you've seen these already when we talked about the scalar product of Rn, because that was an inner product space. Well, this is actually going to go for all inner product spaces. So including the scalar product, but also the other ones we've seen. So first off, we can define the norm of a vector. So the norm of a vector for an inner product space is going to be defined as the square root of the inner product of a vector with itself. So that's going to be standard no matter what inner product space you have, and whatever mapping this is, this inner product, the norm is always going to be the square root of the inner product of a vector with itself. Okay. We can also say that two vectors, so if we have an inner product space, and we have this inner product, then we can call two vectors, u and v, in capital V orthogonal if the inner product of u with v is equal to 0. So it's exactly what you think of when you think of two things being orthogonal. Usually it's u transpose times v when we're in Rn, but now these may be matrices that are m by n, but when we take the inner product, whatever that inner product is, whatever we've defined it to be, where this u and this v could be like polynomials like we just saw, or they could be continuous functions, as long as when we take these two vectors and we take the inner product, we get 0, then we call them orthogonal. We also have something called the Pythagorean theorem. So if you have two vectors u and v in capital V, and they're orthogonal, they have to be orthogonal, then you get the Pythagorean theorem, which is the norm, or the length of u plus v squared is equal to the norm of u squared plus the norm of v squared. Just like a regular right triangle, except for now these are like functions, which, that's not what you think of when you think of a vector. You usually think of things in Rn, but that is a vector space, a space of continuous functions. So this is just a more general definition of the Pythagorean theorem. Now we're dealing with vector spaces. Another property of inner product spaces is the Cauchy-Schwarz inequality. And the Cauchy-Schwarz inequality says that if V is an inner product an inner product space, and you have two vectors u and v in that vector space, then the norm of u plus v is less than or equal to the norm of u plus the norm of v. And you've probably seen this one before. This is called the triangle inequality. And that's a nice property of an inner product space. Okay, let's move on. The next thing I want to talk about is a normed linear space. So usually when we have a norm, we define it in terms of an inner product. Like we said before, we had that if V was an inner product space, we define the norm of a vector x that belongs to the vector space V as the square root of the inner product. And that's one type of norm. But you can actually define a norm without having an inner product. And that's what we're going to talk about now. So a normed linear space is a vector space V with a real number. So we're associating a real number to every vector that satisfies the following conditions. The first condition is that the norm of a vector is greater than or equal to 0 for all V in V. And if the norm of a vector is equal to 0, this only happens if the vector itself is 0. So this is very similar to an inner product space. In fact, this has to be true for inner product space, because remember that the norm is defined in terms of the inner product, and we want that inner product to be greater than or equal to 0, and we want the inner product to be equal to 0 only when the vector is 0. So that has to be true. The second thing is that if you take a scalar and multiply it with a vector, and then take the norm of that vector, it would be the same as just taking the norm of the vector and multiplying it by the absolute value of the scalar. And then the last thing you have to satisfy is the triangle inequality. So if you don't have an inner product, or you don't want to attach an inner product, you don't want to deal with inner products for a vector space, then you can just define this mapping, which takes every vector to a real number, and we call this mapping the norm of the vector. But the mapping has to satisfy the following conditions. So the first condition, where the norm of the vector always has to be greater than or equal to 0, and it's equal to 0 only if the vector itself is 0. That when we multiply the vector with a scalar, it's the same thing. Like if we take the norm of that, it's the same thing as taking the norm of the vector and multiplying by the absolute value of the scalar. And then the last thing is the triangle inequality. So that has to be satisfied. So one example of a normed linear space, remember that is what we're calling this, a normed linear space, is an inner product space. So if we have an inner product space, then we can just define the norm of every vector as the square root of the inner product of the vector with itself. Now this is a normed linear space, and you can check those three properties. So you can check that for every V, this is greater than or equal to 0, and is actually equal to 0 if and only if the vector itself is equal to 0. And that just comes from the actual definition of the inner product, and you can check the other two as well. So you can check that when you put a scalar in there, the scalar comes out by absolute value of it, and then also check the triangle inequality. And this is going to be a normed linear space. So an inner product space is also a normed linear space. let's talk about some other norms. So we know that V is a vector space, this Rn, and the vectors in V look like this, where we have x1 through xn. And this, you can make it into an inner product space, and we saw the different ways we could do that. We could just say, this is equal to x transpose y. That's one way to do it. And we also saw we could write it as x transpose p times y, where p is a positive definite matrix. That was another way to define an inner product. But we can just not worry about that at all and define a norm without the inner product. And one way to define the norm, remember, you want to think of a norm as the length of a vector. And there's different ways to measure the length. And here's one way. This is called the one norm. And that's why I have a little 1 here. So when you see this 1 here, this is what you're going to think of. It's going to be the sum of the absolute value of each entry in your column vector. So for example, let's say you have the vector 3, -1, -5, 2. Let's say this is x. Then the norm of x is just 3 plus 1 plus 5 plus 2. I'm just summing up all of the absolute values of these entries. So that is 5, 6, 7, 8, 11. So that's one way to measure the length of this vector. And you can check that it satisfies those 3 properties. The triangle inequality, the property where you can take the scalar out, and the property where for every vector the length is greater than or equal to 0. Another example of a norm, another way to measure the length of a vector, is the p norm here. And this is kind of similar to this one. We take the absolute value of each entry, but then we raise it to the power p. We sum all of that up, and then we take the pth root of that. So actually, if you just think about the 2 norm, this is the regular norm defined in terms of the inner product, because the absolute value of something and then squaring it, you don't actually need to take the absolute value, right? Because you squaring it is going to be positive anyway, and you're summing the things up, and then you're taking the square root of it, which is exactly what I have written here. So the 2 norm is actually just the regular inner product norm. But you could do other things like, let's take this vector here. X is equal to 3, -1, -5, 2. Then if we take the 3 norm, this is the 1, we're going to raise this to the 1/3, and we're going to have 3 cubed plus 1 cubed plus 5 cubed plus 2 cubed. I'm taking the absolute value of each number and cubing it. I would sum them up and then take the raise it to the power 1/3. Okay, and that is also a norm. And so you could check the 3 properties to make sure that with the vector space Rn with this norm is a normed linear space. Another type of norm, I actually like this one. This is called the soup norm. And what you do is you take the maximum entry, the absolute value of all the entries, and then take the maximum entry, and that is what we're going to call the length of the vector. So our vector x was 3, -1, -5, 2. So under this norm, we would say the length of this vector is 5, because the biggest number, if you take the absolute value of all of these, is 5, and so that's going to be our length. And before we conclude this, I want to talk about something interesting. In a normed linear space, we have something called a unit ball. And a unit ball is the set of vectors, all vectors in your space, your vector space, such that the length of all the vectors is less than or equal to 1. Now, what the unit ball is going to look like actually depends on the norm you're using. For example, let's say we're in R2, because it's easy to draw and visualize what we're doing. What does the unit ball look like? So I should put that. Look like with the norm, just the regular inner product norm. So this is the sum, I is equal to 1 to 2 of xi squared, and then we take the square root. What would that unit ball look like? Well, we want this norm, which is the square root. I is 1 to 2, because we're in R2, that's why I'm only going to 2 of xi. We want that to be less than or equal to 1. So we can square both sides. So if we square both sides, we get that the sum of the xi's is less than or equal to 1 squared, which is 1. And I'm going to actually write this out. Oh, I think I forgot the square here. Sorry about that. So let me repeat what I said. So we had the square root of the sum from 1 to 2 of xi squared is less than or equal to 1. It says we're taking the norm of the vector and setting it less than or equal to 1. But then we can square both sides, and 1 squared is 1. And I'm actually going to expand this. This is x1 squared plus x2 squared. And you can say that this is the x1 axis and this is the x2 axis. And what would that look like? Well, this should remind you of this formula, which is the formula of a circle filled in. Right? If it was equal to 1, it would just be the unit circle. But because we can also be less than 1, we fill this in. So this is the unit ball with this particular norm. Okay, nothing strange there. But what does the ball look like with this infinity norm? Now remember that this is the max. Now we're in R2, so the vector looks like x1, x2. So the max from 1 to 2 of the absolute value of the xi's. And the unit ball is the set of vectors x such that the length of x is less than or equal to 1. Okay, so what does that tell me about my values for xi? I want the max to be less than or equal to 1. And that's the absolute value of the max of what's inside this vector. So that tells me that my xi's have to be less than 1 and greater than or equal to -1. So then my unit ball, we could have the vector, let's say 1, 0. We could also have the vector 0, 1. We could have the vector -1, 0 and 0, -1. But we could also have the vector 1, 1. So if x is 1, 1, then this infinity norm is equal to 1. And so that would belong to the unit ball. In fact, the unit ball would look like a square. So the set of all vectors that have length 1 or less is this square in R2. If by when we say length 1, we're talking about this infinity norm or the sup norm. Let's do one more. In R2, what does the unit ball look like with this particular norm? Now you can check that this is a true norm. You can check the 3 properties of a normed linear space. But I'm going to just say, this is a norm, so you can believe me on this. Let's say this is how I measure the length of my vectors in R2. I take the first entry, I square it, and then I take the second entry, square it, and multiply by 4, add them together, take the square root. Well, the unit ball is a set of vectors such that the length of x is less than or equal to 1, which would tell me x1 squared plus 4x2 squared to the 1/2 is less than or equal to 1. And again, you can square both sides. Square 1, you get 1. So now I have x1 squared plus 4x squared is less than or equal to 1. And if I substituted this with x and y, does this look like an equation you've seen before? It should. It is the equation of an ellipse. So the ellipse, I believe, would look something like this. And this would be the unit ball, all the vectors of length 1 or less under this particular norm in R2.